All right, let's have a look, homework stuff. So here,
I mean.
number 6 on the homework, do we want to go, we want to go through this one?
Yes.
Okay, all right, let's have a look. So first of all, it's asking for a second derivative here, right? Remember, that's our goofy notation for second derivative.
I didn't know that's what that meant.
Right, so, okay, so first things first then, we know that
It's a little easy. I didn't know.
that's how we say second derivative, that's how we say second derivative, or this is kind of weird, but that's how we say it
So
as,
then why is the squared in the denominator over the x and not over the d?
it's just how we do it. I don't know.
That's weird. Because I probably would have extrapolated the second derivative if it would have been over. But
Gotcha. No, that's, I've thought about that before and kind of convinced myself that it made sense, but I can't remember what I convinced myself. Just accept that as the notation. It's not important.
don't ask.
Yeah. No, you can ask questions. That one, I can't remember. That's just how you,
Do not
that's
question
how you
the
write a
math.
second derivative. Okay, so we gotta, this is gonna be one where, okay, we're gonna have to use product rule, right? So that's, this assignment obviously kind of focused on product and quotient rule incorporating chain rule, right? So here we got another problem like that. So y prime, first derivative, is gonna give us what then by the product rule? And we'll just, how about if we just group the 3x together as one of the functions? So we're gonna get 3x times the derivative of sine x squared, which is a chain rule issue, right?
Yeah.
So derivative of sine hand is cosine hand, and then the derivative of hand is 2x. Okay, good. And then we get plus sine x squared times 3.
3.
Okay. Okay, so we could just clean that up just a little bit here. We could consolidate here. We're gonna get what, a 6x squared cosine x squared plus 3 sine x squared. And so this gets kind of messy now, right? Because now, when I differentiate the first derivative, I've got 2 terms. I'm just going to differentiate term by term. So I'll differentiate the first term first, but I've got another product rule in that first term, right? So y double prime then equals from all this, what do we get? And we'll just, how about if we just group the 6x squared together?
6x squared.
6x squared. The derivative of cosine hand is going to be,
Negative sine.
there you go, good. So negative sine hand times 2x plus cosine x squared times the derivative of 6x squared would be, okay, good. So that's the derivative of the first term, right? So now we've got the next term, right? We have the derivative of the next term. So that's all just from that, right? Okay, but fortunately, this one's not so bad, right? This one's just a one-layer derivative. Well, actually, no, it's not. We have chain rule, but it's not a product rule, at least, right? So we get 3 times, what's the derivative of sine hand?
Just cosine.
Times 2x. Okay, good. So now we're done. We just have to pull a bunch of stuff together, right? So what do we get? If we clean these terms up, we get a negative 12x cubed times sine x squared plus 12x times cosine x squared plus 6x times cosine x squared. But look at that right there. What do you notice about that? Yeah, those are complicated, but they're like terms, aren't they? Right? I've got 12 times that plus 6 times that is 18 times that, right? By that, I mean x cosine x squared. Okay. We recognize those like terms, everybody? Okay. So, so what can we do then? I guess we could factor out a 6x if we wanted to, and we end up with then I always put the positive term first, so the negative goes, it acts like an operation instead of just a sign out front, you can forget. That makes sense? I mean, you don't have to do that, it's just personal bias. So then that would give us a 3 cosine x squared minus a 2 x squared sine x squared. That's about all we can do. Right, and once again, all I'm doing here is just changing. Okay, so that's good practice. I mean, and the fact that that's a second derivative just makes it tougher. Okay, what else? Any other ones that were particularly problematic you want to take a look at? Want me to scroll down a little bit?
Yeah. Just trying to put this all together. So the, so I have a,
Can you do number 5?
Mm-hmm. Something like that?
Yeah.
Yeah, okay, this is a good one to talk about. Yeah, I think this is good. Okay, so in fact, I would say it might be a good deal for everybody to just pause for a second. Let's just at least talk about how we could approach this one, right? So what are our options here? I mean, right now, this is sort of inconvenient because we've got a power rule and then the next layer is a quotient rule inside the power rule, right? Okay, what could we maybe do with this to make this at least a little bit sensible?
We change it so it's probably.
Okay, we could, that's fine, we could do something like that. So another thing we could do is, we can always look inside the outer layer and see if anything could be simplified inside the function. So let's focus on this part in here.
Take out a T.
Yeah, I could cancel a t from the top and bottom, couldn't I, right? Could factor a t out of the bottom and cancel it with a t on the top. Can we see that? So then we end up with the quantity inside, we would just get a t divided by a t squared minus 4. That's quite a bit better, right? Okay, and now we could just proceed with that, and do, yeah, it's fine. We could do the derivative of hand cubed is 3 hand squared, and then the derivative of hand is going to give us a quotient. Or the other option is, if we wanted to, and that's fine. I don't know that there's a huge advantage either way. The other option is, if we wanted to, we could rewrite this as, what if I were to take advantage of this property of exponents? If I have a over b to the m, what's that equal to?
A to the m over b.
Right, so that would give us here t cubed over the quantity t squared minus 4 cubed. And at least then, I can't guarantee that's going to be tremendously beneficial. What's the one advantage of that? Well, now you just have quotient rule, right? Inside the quotient rule, you're going to have some chain rule stuff, but yeah.
Could you change that then to be, particles and make
Yeah, and then
it
you
t
could,
squared
right,
minus
so
one
you
negative
could,
third?
and you could write that as t cubed times the quantity, t squared minus 4 to the negative 3, and just use product rule too, yeah. Okay. And that probably is the easiest way. And then if you do this with a product rule, and we've done a bunch like this, then you kind of predict what's gonna happen. What are your bases gonna be? And you're gonna get t's to some powers, and you're gonna get t squared minus 4s to some powers, that you can factor out the least common factor, right? The least power of each base, we'll just factor out front. Okay, I mean, do we wanna, we wanna do this? Okay, so let's take it from here. How about if we go from that form right there then, what are we gonna get? So that's y. So by the product rule, y prime is just gonna be t cubed, right, times the derivative of that stuff. Okay, so what's the derivative of hand to the negative 3?
-3 and to the negative 4.
Okay? And then the derivative of hand, we look inside, just everybody agrees 2t.
Yeah.
Nice thing about this though, is then it's just plus. T squared minus 4 to the negative 3 times the derivative of t cubed is what?
3t squared.
See, that's not horrible, right? And if we just clean that up just a little bit before we factor, what are we gonna get from this first term? Negative 6t to the 4th, right? Times t squared minus 4 to the negative 4 plus 3t squared times t squared minus 4 to the negative 3. Okay? And now we got bases here, right? We've got bases of t and bases of t squared minus 4. Okay? And what number could we factor out?
3.
3. We take out a 3.
3.
So if we're collecting a bunch of stuff out front, we've got 3 out front. Now what's gonna be, what power of the base t can I factor out?
T squared.
T squared, right, the least power. Okay, so we take out a t squared. What power of the t squared minus 4 are we taking out? What's smaller, -4 or -3? -4 is less, isn't it, right? So we'll take out a t squared minus 4 to the negative 4, and now what's left behind? So we're gonna get, what number's left from over here? -2, right? We're factoring a 3 out, so we're dividing -6 by 3 and getting a -2. We're left with a
T squared.
t squared, and so that's factoring out completely, isn't it? Right? Plus 3's completely gone. Whoops. The t squared factors completely out, right? And we're left with this base to what power?
1.
The 1. Right? Let me pause there. Questions?
On that question? The question.
And then, now, we can finish this, but I mean, does that make sense? So now we would just, we can simplify this factor and write this as one big rational function, so a bunch of stuff on top, bunch of stuff on the bottom. What do we end up with on top? Well, we've got a 3t squared on the bottom, that goes to the bottom, doesn't it? It's a negative exponent, so on the bottom, we're getting t squared minus 4 to the fourth. And then what's happening to this whole thing in here? You're getting a negative 2t squared plus t squared is a negative t squared minus 4. Do you agree? And what should I probably do with that? Maybe take out a negative. So my final answer then just looks like negative 3t squared times t squared plus 4 over t squared minus 4 to the fourth. Yeah, that was a pretty good way to do it. I mean, we could have done it other ways. But if you had, I mean, think about what this would have looked like. It would have been horrible, but if we had done this just as is, even if we divide top and bottom by t, I'm going to get a 3 times this quotient squared times the quotient rule. Probably just slightly messier that way. Okay. But it would work. It would work also. You're going to get the same place either way. Okay. This stuff is just, I'm telling you, this is such good practice. This is what it's just kind of what it takes to get on top of this. You know, it's just a battle over and over again until you start to see the patterns and it just starts to get easier. And then after a while, it just seems like it's a lot easier. You know? But you gotta, it's just all about getting some practice. It really is. That's a lot of what calculus is. And then we'll add some context to it soon. Right? So I think we need to start thinking about, you know, we're probably getting close to where we maybe need to take a test or two on this stuff too, right? Because before we jump into the applications, I think this is a good place where I think what we've done here, we've really just added, since our last test, what have we done? We've just added some differentiation rules, and we've added chain rule. And so, you know, I'll put up a review. Let's finish the log stuff up. So all we're really going to do with the log stuff, I'm going to give you just a review assignment. You know, we'll finish up our review of logs. Not anything we're going to test over, but I'll give you a review assignment on just property of logs. So I think it's good to get a little practice with that. We'll kind of finish talking about the pre-calc stuff. And then all we're going to do with the logs at this point is just add a couple more, you know, standard forms for our derivatives. We're going to add to our list of derivatives we can take the derivative of a log function. And it's no big deal. And we'll get a little practice with it. I'll give you a short assignment on that to practice it. And then that's probably a good place for us maybe to take a test. And I'll break it into a couple parts so it's easy to retake. Okay? That sound good?
Yeah.
Okay. So then, let's maybe just continue on with our log review from yesterday. So now I'll maybe have you click and close. So we were looking at properties of logs. Remember our way of thinking about this too, and I think this is a good way to organize it in your mind. When you use these properties of logs, you're just working your way down the order of operations tree, right? That's the advantage of harnessing the power of logs, is they make the arithmetic relationships one rung easier on the order of operations ladder, right? And we want to take advantage of those. So just a couple more things to practice then, like how are we going to deal with this one? How do I simplify the natural log of 2 to the negative 1?
Negative 1, natural log 2.
And we're just taking advantage of the exponent property, right? And that's really the same thing we did there, isn't it? Right? 2 to the negative 1 is the same as 1/2. Okay, now this is an important one. What about this? The log of x to the fourth.
For
It doesn't quite fit, does it? Right? Because the property, think what the exponent property is. The exponent property is the natural log of a to the n equals n log a. Where are the implied parentheses there, though?
About around the A.
Around the a to the n, not around the natural log, right? So the important thing to recognize here is that this one doesn't simplify. There's nothing you can do with that, right? This is different, though. that's a different question.
Yeah.
You see the difference? What would that be?
4 natural
Four.
log.
There we go, 4 log x, right? Okay. What about that? Everybody, now, don't say it out loud, but let's everyone think about that one for a second. There's really two things going on. And we can write an intermediate step at first, but then I would suggest after that, you really don't have to. You can just jump right to an answer, but really, there's two things going on, right? I've got a quotient, and in the numerator, there's a product, right? So if I apply the quotient rule first, I've got the natural log of xy minus the natural log of z, but then what's the log of the quotient?
The line.
It'd be the log of a product is equal to the sum of the logs,
Yeah.
right? So log x plus log y minus log z. And really, I think you can just make that jump in one step, okay? How about something like that? And let's see, just stare at that for a second. And we can do that in many steps, but let's just see, and this is really good for your brain, this is a mental workout. See if we can simplify this thing too. While we're at it. So what are we thinking here? What am I gonna do with that? What's the outer level of this thing?
What's that 3?
It's a log of something, log of hand cubed, right? And what's a log of hand cubed? That's just 3 times log of hand, right? So we've got a 3 out front. But why might I open a set of brackets there?
Because
Yeah, because that's complicated, isn't it?
Yeah.
Right, I'm getting a 3 times the log of all this stuff, but that's a lot of stuff, right? That's a quotient, so then what are we gonna end up with in the brackets? I've got some stuff on the top, so I've got the log of the top minus the log of the bottom, but what's the log of the bottom gonna be? A log of x cubed is the same as a 3 log x. Okay, good. I double dog dare you to go one step further with that. Anybody see one other possible way you could get something out of that?
The ln of natural log x.
Yeah, what about this one? Now, you gotta be careful with this, because what's the log of a sum or a difference? You can't do anything with that, right? We're already at the bottom rung. So there is no, and remember, if we go back, I wanna quickly just go back to our previous page here. Remember, like if we have something like this, the natural log of a plus or minus b, the answer is the natural log of a plus or minus b. You can't split that one up, right? But there is, I don't think I even, if I remember, I don't think I even maybe intended it to be this tricky, but there is one more step you can go with that. If you really are tricky about it.
that x plus 1.
What could it be? There you go, good. What is x squared minus 1? That's a product, that factors into x plus 1 times x minus 1. Everybody see that? That's pretty good, right? So we could split that one, oops. Right, so we could actually just split this guy right here into a log of x plus 1 plus a log of x minus 1, because that is just a log of the product of the two, isn't it? Right, so our final answer then would look like 3 times all that minus 3 log x. Okay? And that's best part you could go with before. Okay? So last little part then. Well, I guess we'll do one more of those. And all these have been, think about all these that we've done, because usually this is what we do with logs. We're trying to simplify a log, right? So what about this last one right here? Take a second and digest that. do you think? What's gonna be the first part of this? 1/2, good, we have a 1/2 power to it.
Yeah.
Okay, good, so we're gonna get a 1/2 times a bunch of stuff. Okay, what's the stuff?
ln x
So log x
plus log y
plus log y
minus 4 ln.
There you go. Yeah, you guys got this. Good. All right, so last one then, let's go the opposite direction now. Let's consolidate. Okay, rather than expanding this, let's consolidate this into one complicated log. So now we're kind of reversing the direction we're doing this stuff, aren't we? We're kind of working from the inside out a little bit. So what's gonna be the relationship? Like, well, what's this part right here gonna give me? What's that gonna do? So that's gonna be a natural log x plus 3 squared, okay?
Times x.
Okay, times x. Right?
Divided by.
Okay, good. Divided by log x squared minus 1. And then finally, that whole thing is just gonna make it a cube root of the whole thing, right?
Yeah.
Or 1/3 power, either way. Okay, good. All right, so let's go ahead and talk about the derivatives then, okay? There's a pretty cool way, I would think, I'm not gonna do it today. Let's just, for today, let's approach it this way. Let's just, I'm gonna give you the derivatives, and we'll practice using them just a little bit. But there's a pretty cool way that we could make a prediction of what this is supposed to be too. And I feel like that's just a little bit much to throw at you today on top of all this. That's like filling the glass too full. But we'll come back and do that a different day. Just talk about how we can make that connection. It's pretty cool. But here's our rule that we get then. The derivative with respect to x of log x is just 1/x. Okay. Now what's the caveat here though? For if it's a log function, what's the domain of a log function? X has to be greater than 0, right? Because what's the graph of a log function look like? Just quick review. Right, so what's that look like? Remember, so it can be the inverse of the exponential function, right? Asymptotic on negative y. It's just doing that, isn't it? Right? So the domain is going to be x is greater than 0. It's not defined for x less than or equal to 0, right? Okay? That's why we have to include this. Okay, so then what's going to be the chain rule equivalent of that? So the derivative of log u, 1/u times the derivative of hand, which would just be a u prime. We don't know what, I mean, u is like hand there, isn't it? We don't know what u is. It could be x squared plus 1, who knows, right? Times u prime. And a better way to write that would just be u prime over u. Okay? So let's practice that a little bit. So what if we have something like, and then, now I'll give this to you too. So then, in order to ensure that the argument of the log is positive, one thing that you can do is you can take an absolute value of what you're taking the log of, right, to make it positive for sure. What does that impact? Nothing. The rule is the same. U prime over u. Okay. So let's practice this a little bit. So now what if you have something like the g of x is the natural log of x squared. Okay, let's use our new standard form. The derivative with respect to x of log u, we said, was u prime over u. Okay, so what's that going to give us? What's u prime?
2x.
2x over,
X squared.
which simplifies to, okay, what's an alternate way of doing this one that's really, avoids having to even use the chain rule version? What could I have done to my original,
You
the
could
argument of that law? How
get
could I
two
sim-
out front,
I could, yeah, I could simplify the whole thing, couldn't I? I could just
Yeah.
rewrite that as
then you get 2 log X.
2 log x, and that's 2 times 1 over x then, right?
Yeah.
So there's either way. Okay.
Ah.
See what I'm saying?
Yeah.
Okay? Which way is generally better? That way. Use the properties of logs to make it simpler before you do the calculus. Doesn't it make sense? I mean, when we're doing derivatives, don't the derivatives get complicated sometimes, right? But it's, you'd rather start with something that's relatively simple before you differentiate, right? So what about this guy?
Take
I mean, we could do this, we could hammer through this and use this form, but that's gonna be a little complicated, right?
Yeah.
I think what's gonna happen, you're gonna get u prime, which is gonna be complicated, divided by that whole thing. That's gonna be pretty bad, right? I'm gonna end up with a square root on top, I'm gonna get some complicated radical on the bottom, and I gotta simplify all that stuff at the end. Doesn't it pay off instead to just take advantage of our properties of logs we've been practicing? So what is that gonna be? Before I even do any calculus, what am I gonna end up with there?
1 natural X plus 1 minus the natural log of X minus 1.
Now, that might look worse, because there's a bunch of terms there, but that's a way easier derivative, isn't it? Right, so if I'm gonna differentiate that, what are we gonna do? What about the 1/2?
It'll hang out.
Everybody get that? Just a constant, we just leave that out front, right? The 1/2 will just hang out front. And how come? Because when we take a derivative of some constant times f of x, what do we get? Well, we just get some constant times f prime of x, right? The constant just stays out front. So we get a 1/2. And then what's gonna be inside? Well, what's the derivative with our new rule? What's the derivative of the log of x plus 1? I get u prime over u, so I'm getting hand prime. What's the derivative of x plus 1? 1 divided by hand, right? Minus the derivative of x minus 1
1.
over,
X minus
1.
that's it. Right? And if we wanted to, we could, we could combine these, get a common denominator and combine those into a single fraction. That's not too bad though, a lot easier than the alternative, agreed?
Yeah.
That would have been pretty bad, right? What about this one? We're definitely gonna wanna simplify if we can, untangle that thing before we try to differentiate. So I got a quotient, don't I?
Yes.
Okay, so Evan, what am I gonna get on top here? If I'm doing the log of a quotient, on the top I've got the log of the top minus the log of the bottom, right? So I'm doing a quotient.
Yes.
What's the log of the top gonna be?
1/2
Log of-
natural log
Okay.
plus X.
1/2 natural log 4 plus x squared, everybody agree?
Yeah.
Okay. Minus log x. Okay. And now we can differentiate that term by term. It's not terrible. First term, we've got a 1/2, and what's our rule gonna give us here? Derivative of log u is just u prime over u. What's u prime?
2X.
Okay. Over
4 plus X squared.
any cancellation,
2's a
right? So there's our first term,
cancel.
minus derivative of log x.
1/3.
Okay. Good. What about that one? What do you think about that one for a second? Function's the log of log x. I can't simplify that, right? We don't have any crazy property of logs when I take a log of a log. But I can follow my rules. So let's think about that. The derivative of log u is u prime over u, right?
Yes.
Well, if u is, something bad grammar, if u is log x, what's the derivative of u then? What's u prime? What's the derivative of log x? 1 over x? Okay, so that's what's on the top of the fraction then, right? That's gonna be my u prime is 1 over x. And what's on the bottom, right? So if I were to simplify that then, that's like saying 1 over x times 1 over log x, right? Make sense? Okay. Not a ton I can do with that one, is there? Because look, I've got a log on the top and a log on the bottom. It's not a log of a quotient this time, right? So I'm sort of stuck with that. You could maybe use Emily's trick and break that into a log x plus 1 plus log x minus 1 if you wanted to. That would maybe help a little bit. But you're sort of stuck, this time you're stuck with a quotient involving logs, right? Okay? So by the quotient rule then, let's just kind of wade through this one, right? We've got low v high, so I've got the bottom times the derivative of the top, right? So the derivative of the top is going to look like u prime, what's that? 2x divided by u, which is x squared minus 1, right? Minus high v low. What's the derivative of the bottom going to be? So I have the derivative of, now my u is a 4x plus 1. So what's u prime? 4, okay. So I've got a 4 divided by 4x plus 1. All divided by the bottom squared, right? 2. And this time, I'm squaring the whole thing, right? So it's not really a log of 4x plus 1 squared, it's the whole log squared. Okay. And, you know, and so, when are we at? 25?
Yeah.
Okay. So to simplify this one then, look, you know, it's kind of a mess, isn't it? We're gonna have to get on the top, yikes, we're gonna have to get a common denominator. I mean, this is pretty messy, right? So on the top, if we, let me go to the next page. There it is. So, I mean, this is getting pretty bad. If I write that as one fraction, I've got a 2x log of 4x plus 1 over x squared minus 1 minus 4 log x squared minus 1 over 4x plus 1 times the reciprocal of the bottom, so we're multiplying by 1 over log of 4x plus 1 squared. You're probably thinking, man, that's going to be horrible to simplify. And realistically, I mean, this is one where you'd only simplify it if it made sense. Like, what if all they were asking here, and I mean this too, like, what if all they wanted you to do was find the slope of a tangent line, or find the equation of a tangent line? Why would you ever simplify that? Right? Because all you're trying to do is plug in some value of x into the derivative and get a number back. So you would never want to waste time doing that. The only time you'd have to really simplify this is if you were trying to find, you know, all of the zeros of the places where the derivative is equal to 0 or undefined. And then you'd have to just crank through this thing and get common denominators. But you really do want to think about that stuff in advance. Only go further if you need to, right? I mean, if you're just trying to get some numerical answer out of it, you won't do any simplifying. Just plug in a value, and it's easy to put numbers into those and simplify, right? That's not a big deal. It's hard to simplify this algebraic. Okay, that's a pretty tough.
Yeah.
Yeah. Okay. All right. Good place, Scott. Okay, I'll put a little review assignment up.